we're not done yet. We haven't heard anything about squid. And who better than to discuss the wonders of the cephalopod world than Jaron Lanier, inventor of virtual reality, brilliant musician, best-selling author, technological visionary.
Hey, thanks, David. No, I'm not going to do that. My hair just projects. It doesn't work. So, is this working? Yeah. Okay. So I'm going to start by talking a little bit about virtual reality history and how it bridged into some research in neuroscience and linguistics, and then from there to the weird stuff with cephalopods. Is that good? And all right. So I'm going to take you back a very, very many years, over 30, to Silicon Valley. In computer, it's like dog years, your computer years are like that. When I was 40, I was lecturing at the Stanford Computer Science Department, and this undergraduate came up to me and said, "Jaron Lanier, you're still alive?" I'm only 40, and now I'm over 50, so so in the computer world, I'm really antique. I'm really this relic. But anyway, back at the start of virtual reality, we were putting people in these goggles and gloves, the classic VR stuff, and when you connect multiple people together, they have to see something of each other, and thus was born the avatar. So we had these computer versions of people moving around, and this was initially revelatory because in those days computer graphics was really, really bad. Initially we just had these lines made of little squares. Of course, the pixels were huge, and then they gradually turned into sort of origami or plasticine shapes, and gradually started to take on a little more detail. But even when they were horrible, just seeing the motions of other people was utterly revealing of the people. It turns out if you can just see a little bit of somebody's motion, you can tell a lot about them. You can identify individuals, you can discern their gender and their mood, their intent. Even just a few dots of somebody moving. There's a hidden motion language between people. This had been known before from some other experiments, but it was never revealed quite so dramatically as in early virtual reality. And this hidden motion language is going to turn out to be important, as you'll see. Now, one day in the lab, I experienced a bug. And of course, in computer science, bugs are the history. I mean, bugs are what always reveal something new. So in this particular bug, my hand and my arm became gigantic, like a huge crane, like a fantastically huge crane. And as it happened, I was in a model of the city of Seattle at the time, and we had this project with the Harbor of Seattle to help plan a harbor. So I just had this gigantic hand, and I remember looking up at it, and it was the most amazing experience. And now the fun thing to do if you find yourself with a gigantic hand is to curl your fingers and see this huge finger rushing up and then swallow you so you're inside your fingertip. And for many months, that was like the trippy thing everybody wanted to do when they visited the labs. Like, oh, I have to do that thing where you get inside your own finger. So we had a lot of trouble with those demos because when you do this kind of work, there's like this crowd at the door, I want that demo, and then you can't do any work. You're like, we have to work someday, what do we do with this whole thing? So then one day, I was, after having gotten a little tired of being inside my own finger, it does happen eventually. I started playing with other things that might be done, and I discovered that to my amazement, I could actually control where this giant arm moved in Seattle. I could pick up individual little ferries, and I could pick up little houses and cars, and it was very strange. Now, in order to understand how weird this is, you have to understand how easy it is to make dysfunctional virtual worlds. It's very, very easy to make unusable, horrible virtual reality experiences. It's one of the easiest things you can do. To illustrate this story, and since we're in a film school facility, I'll tell you a story based in the movie world. So around the same time, I got a call from a friend of mine who was already a well-known director, but still young, like me, named Steven Spielberg. And he said, we've got to introduce Hollywood to virtual reality. you've got to bring some of those virtual reality systems down here so we can show all the Hollywood people. And I'm like, hey, we're Silicon Valley. You come up here. You know? And he said, no, man, we're Hollywood. Silicon Valley has to come to us. And I said, hey, we're going to copy your files. You come up here. And like we did something. And finally he said, hey, we'll pay you a lot of money. He said, oh, okay. We packed these virtual reality systems in a big semi-truck, and it was called Reality on Wheels. And we drove it down to LA, and we parked it for a week at Disney and a week at Universal. And these were the two studios that also had theme parks. And at Universal, there's one of these classic studio bosses still alive running the place, and his name was Lou Wasserman. Anybody know who that is? It's interesting in different audiences. I figured here there would be people who would know. Well, of course, to many he's an unknown. But anyway, so Lou Wasserman is watching all these people go through, and they're turning into beetles and doing all these weird things. And he said, hey, kid, come up here. And there's this finger. And I'm the kid. And I'm this really bubbly, energetic, ambitious kid, 20-year-old or something. And, yes, Mr. Wasserman, how can I help you? Hey, kid, are people going to throw up in this thing? And I said, oh, Mr. Wasserman, we have been studying this problem. We have a collaboration with these researchers at Stanford, and we have it down to only one instance per 10,000 now, but we're going to have it down to 1 in 100,000 next year. This is not a problem. We understand it. And he looks at me like I'm an idiot. He says, kid, you don't know the first thing about entertainment. And he looks over at Spill and says, who'd you bring me? He says, look, kid, I want to see headlines in the paper that my janitors are quitting because they're sick of the vomit. I want to see the union picketing the site where this thing is over the vomit. Okay, now I want you to come back here when you know the first thing about entertainment. Okay. Now, many years later, I designed gadgets for this other movie that they called Minority Report, which you probably remember. You know, you talk to undergraduates on, they haven't heard of it. So ancient. And so anyway, in Minority Report, I would design these gadgets, and the scriptwriters would play around with scenes. And so there's this one scene where they're saying, well, maybe we could use eyeball biometrics for something. And I said, well, we could have the criminals steal the eyeballs. And Spielberg is like, oh yeah, then we'll have these disgusting scenes where the eyeballs will be rolling down the street and into the gutter, and there'll be these horrible crashes. And he said, this is what Wasserman was talking about all those years ago. He said, yeah, kid. And so, so it was a shock that you could make your hand giant and still use it. Because you do anything in virtual reality slightly wrong and people throw up, basically. That's the thing you need to know about our field. You mess with the human sensory motor loop, and you can really screw people up. All right, so it turns out you could change the avatar drastically, and people not only didn't get screwed up, but seemed to immediately adapt to an altered body. So the next step was to start altering avatars in ever more radical ways. So we started saying, well, could we attach the arm here? What if you're on all fours and you're a gazelle? What if, And then one day, a designer named Ann Lastow came in with a picture of a lobster costume from some lobster festival and said, oh, we have to do lobster. So she made a lobster avatar. And the thing about lobsters is they have these extra little arms on the side. And so, gosh, they're extra arms. So the way we were running these things is you'd wear a full body suit. These were probably the first real-time motion capture suits, and motion capture suits are still used in special effects, of course, but in those days they had their birth in virtual reality. And what we decided to do to control the extra little arms was what's called a virtual parameter. Instead of just mapping literally, from one joint like your elbow to the elbow of the avatar, we would grab a little bit of the range of one elbow and a little bit of the range of your hip and a little bit of a range of your ankle, and we'd mix them together with some arithmetic and then apply that to the middle joint on the right side of one of the lobster limbs. So we're just pulling out we're taking the same amount of data to start with, but just kind of factoring it out so it ends up controlling more parameters. just to screw around. We didn't think anybody could do it, but people could do it. I mean, adults could do it fairly quickly, and children seemed to be able to do it instantly. And it was just, that was really kind of freaky. And so then we started playing around with making weirder and weirder animals, of course. And it turns out we could do some animals and not others. We started developing some hypotheses about exactly what kind of avatar weirdness the human nervous system can tolerate and what kind it can't. And mathematically, we think it doesn't know about quaternions, for instance, little things like that. But sorry, I can nerd out, but I shouldn't too much. But a biologist collaborator of mine, with whom I was making some models of parts of the cortex from Caltech, named Jim Bauer, was visiting, and he said, "You know what you're doing? You're exploring the space of pre-adaptations of the brain, and you're also exploring its deep past." And we suddenly saw the research in an entirely different light. So let me explain this. Everything in biology is pre-adaptive, meaning you don't know how it'll be used. So referring to the last presentation, you might end up peeing on a fire to put it out, even though the penis wasn't evolved for that, so far as we know. And it's a great example. So in this case, going back tens of millions, hundreds of millions of years, our brain has evolved through multitudes of species, at each step having a little bit of pre-adaptive capability to be ready to gradually morph into the next species. And we're just one point in this long, long progression in deep time. So our brain has essentially controlled all these different bodies. Our brain has controlled creatures that crawled and swam and swung from trees. And when we turn into a weird avatar in virtual reality, what we're really doing is we're operating a time travel service for our brain. We're letting it experience the deep time of its past, experience all the other bodies that it used to control. But even more amazingly, we're giving it a chance to control the bodies it's pre-adapted to evolve into in the future. So we're giving it a taste of the bodies it's kind of ready to control that we might evolve to in another 50 million years. So if we ever evolve to have giant hands, that's going to work. It's something we couldn't have known without virtual reality. Now, so this is in my view the most wonderful and intense use of virtual reality I've ever discovered. And it's a funny field because virtual reality is kind of familiar as an object of culture, of popular culture. I think there's more virtual reality than sex in the movies. These giant blockbuster movies, Inception and Avatar and the Matrix movies, all these things are kind of virtual reality themed, but it's very hard to experience immersive virtual reality. Almost nobody has. Who here has? Only a few hands. And to experience really good quality is incredibly rarefied. So it's still this very esoteric thing in practice, although we're working to get it there. So when you experience turning into a different avatar, you're using the sensory motor loop itself as a canvas. You're using the way you connect to the world as a medium of expression. And this is something that's quite profound. I think it's the most profound medium yet for human expression. If you look at the popular devices that are out, like the Apple stuff where you multi-touch, just that little act of having a different way of interacting with something has just rocked the world. It's meant so much to so many people, just to have that little experience of a different loop of how you interact with things outside of you. And of course, once you have the full virtuality thing, oh boy, it's going to be very intense. My favorite experiment with weird avatars involves two people, where you hook your point of view into the other person. You see out through their eyes, they see out through your eyes, and so forth. So your sensory motor loop becomes a figure 8. And I dare you to try that without either attempting to kill the other person or falling in love. It will affect the genetic makeup of the species. A lot will happen. It's going to be a big deal. You'll see. Anyway, what can you do with this? What application other than seduction might this be good for? So one of the things that's intriguing is education. So did some experiments with children, mostly like 6th graders. And the idea is not to put them in a virtual world where they're surrounded by simulations of the stuff that might be the subject of their education. And that is interesting. You can put somebody, you can make them feel like they're in the time of the dinosaurs or something, perhaps. And that's all great. But what's much more interesting is to turn them into the thing they're studying, so that their avatar is the subject being studied. So for instance, if you actually turn into a dinosaur, that becomes much more interesting than just being next to a dinosaur. Very, very different. Now, what exactly is different? One thing is the psychological setup, because let us say that both children and people in general are narcissists. People are interested in themselves, so if you become the thing you're studying, what you're studying becomes quite interesting to you. And so a child as a dinosaur is really, really interested in dinosaurs. Now, there's also the fun of it. I mean, you get to be big like a dinosaur. Every kid loves the idea of the bigness. But you can also turn kids into other more interesting avatars. I turned kids into triangles in a trigonometry simulation where they would use their bodies to change the proportion of the triangle, and then they could watch effects and other geometries that were connected to them. I believe we'll be able to have the avatar perform acts of coding and database operations and editing. I believe he'll dance to control your Facebook settings, so you'll finally get it for once. I believe you'll as an avatar, I think you'll turn into molecules to learn chemistry. That one was probably the single most successful and provocative experiment. I've mostly done little molecules so far, like you turn into a sugar or an alcohol or something, little organic molecules. But of course, the really cool ones would be proteins. And so what you have to do is you have to analyze the thing, figure out its degrees of freedom, and then map it to the ones that can be measured from you, just like we did with the lobster. Is it all making sense? And then as a look, you could be, the one I want to build soon is you're an odorant, you're a little smell molecule, and you're approaching you're in somebody's nose, and you're approaching, you're about to be sensed, and you ease up into the little cup, in the little sensor cup. So, all right, so this, one fascinating question to ask here is, can using avatars as a form of communication, as a form of education, open up something new in human abilities? Is it a way to teach what we could do anyway more efficiently, or might we be able to do new things? That's another question. Obviously, this is an experimental science, so I can give you some guesses. We have one early clue that something quite dramatic might be lurking and waiting to be discovered. And that comes from music, actually. How many people can play the piano? Just out of curiosity. So more hands go up than in many parts of the country, I will say. And then how many of you improvise at the piano? So if you improvise at the piano, there's this moment when you have gotten familiar enough with it that you'll notice that your fingers just solved a problem in harmony and voice leading. You say, oh wow, I just got from one chord to the other, and that actually worked pretty well. And then if you record yourself and you go over what you did, you'll often discover that actually for me to explain how I did that takes longer than it took me to do it. There's some way in which your body is calculating in this space faster than you can articulate your calculations in the same space. Now we're used to somatic cognition being fast. For instance, you have to move your hand to where the ball is going to be. Right, so we're used to that, but in these sort of continuous problems that are very typical in the world of motion and the body. In this case of the piano, the body is apparently solving problems of some significant complexity, of symbolic complexity and mathematical complexity, because the rules of harmony are not trivial. To sit there and work out a transition from one chord to another with your brain and a pen is an assignment in a music theory course, but to do it with your hands sometimes can be automatic. Okay, so I have a friend named V.S. Ramachandran, who's a biologist you might be familiar with in San Diego. And he has a hypothesis that new mental capabilities tend to arise in multimodal areas in the cortex, where you have two specialized areas that tend to abut each other, and the circuitry of both kinds of thinking can produce new effects that might be pre-adaptive for something. And so one might think that language arose from such abutments of parts of the cortex. Now, if you look at the real estate on the cortex, the huge majority of it goes to controlling the body. There's the motor cortex is this huge stripe that goes under the place where a mohawk would go, along the top of your brain, and it is sometimes referred to as the homunculus. And it's a mapping of your body, and it's gigantic. And there's all that circuitry just to do this sort of smooth control I was talking about. In places where that abuts parts of the brain that are specialized with symbolic reasoning or with other sort of structured thinking, one might presume that there are capabilities waiting to be discovered. And one might wonder if what happens when you're playing the piano is that you're taking advantage of one of these areas. One might wonder if we don't know. Now, what I'm really interested in is if we bring the body into these other intellectual domains, might we uncover something like what the jazz pianist enjoys? Might we uncover some ability to think differently, maybe better, faster, more intuitively about symbolic domains that have traditionally been very step-by-step and nerdy? You know, might there be some sort of alternate way to program, alternate way to do math, alternate way to do reason that has this kind of flow we associate with music, for instance, or an efficient method. So this is a quest. It's an empirical one, not a theoretical one. We don't know what's going on in there. How many of you have seen the video from Jack Galant's lab in Berkeley in the last few months on YouTube? Do you know what I'm talking about? So this is one of the most dramatic pieces of work in neuroscience, although we don't know quite what it means. So Jack's a friend of mine, and what he did is something very simple, well, complicated to do, but simple to say. He showed a bunch of people videos while they were inside fMRI machines, and fMRI machines are magnetic sensing devices that can tell where the blood is flowing in the brain, so they give you a sense of which parts of the brain are more active at a given time. Very crude measurement, but among the best we have of what's going on in there in real time. So he showed them just a bunch of different movie clips. And then he showed them a new movie clip they'd never seen before, something entirely fresh to them. And he took all the data about how their brain had been activated by the early clips and just performed statistical correlation on the new data as they were watching the new clips they'd never seen before, and tried to use that to infer the content of the new clips. And the images came out. He reconstructed crude versions of what they were seeing. Right? And so you see these sort of really fuzzy, crude movies that are directly reading the thoughts of somebody who's watching them. And the interesting thing about this is it's pure statistics. We still have no idea how the brain represents information. So we have this world of indirect approaches to the brain in which we can perform all kinds of tricks. And the work I'm talking about now is in that category. We're pussyfooting around it, but we can't really see into it. We can't really see the structure. So this should bridge to cephalopods, and indeed it does. Indeed it does. About 15 years ago, I ran into a wonderful marine biologist named Roger Hanlon, who's at Woods Hole, who studies cephalopods. And we got into this journey about cephalopod neurology. So let me give you a very quick introduction to the cephalopods, who I really adore. So these are the tentacled things. I'm told by my daughter and many others that I'm gradually turning into one myself. No, it's not a sexual display. It's an homage to the cephalopods, just to be clear. So the cephalopods independently developed a remarkable neurology and their own intelligence in this entirely separate line from mammals. They have a strategy a little like people, where they're kind of soft and vulnerable from a physical point of view, but they're just really clever compared to the other creatures in their ecosystems. So they're these soft things that have big brains. And they're mollusks. They have to independently evolve brain structures that are remarkably similar to the ones we see in mammals, invertebrates. They have the cerebellum, for instance. They have all these these parts that seem analogous both in form and function. And some of the fancier cephalopods it's not the New York Philharmonic, it's okay. Well, to give you a sense of cephalopod intelligence, in San Francisco where I live, there was once a situation where some nice crabs in the local aquarium were being stolen, and everyone was certain it was a janitor or somebody like that who was just stealing the crabs to eat. So they set up a stealth video sting to catch the perpetrator so he could be thrown in jail. And it turned out to be an octopus crawling out of the tank. Some octopi can actually survive in the air for a bit. Crawling out of the tank, grabbing the crab, burying the evidence in his own tank so that nobody knew where the crab ended up, reclosing the tank. And so it required, this is what's called evidence of a theory of mind. The whole strategy anticipated the detective operation, but not the video camera. Right. So this is like the kid who posts the party pictures to Facebook. You're like, just not quite up to date on what these can do, you know. So at this point, the octopus community is totally hip to this. It's not going to work again. But anyway, these are smart creatures. So the fanciest ones can morph themselves in this remarkable way. And some of the good morphers are a creature called the mimic octopus, and also the giant cuttlefish that lives around the island of Palau in the South Pacific, particularly. Because of my work, I actually got a stamp. I have a stamp in Palau because of my work with the cuttlefish there, so it's probably my favorite honor, except the NJIT thing, of course. Anyway, what they do is they have a display skin. They have pixels on their skin, and these are called chromatophores. And they're cells that can be expanded or contracted very rapidly that have color pigments. And most of them have a 4-color scheme. And in terms of quality, they're comparable to the displays we put on iPads or something. They look good. And they have a fast frame rate. I mean, they're good displays. They're better than our computers had until very recently. And then they have an ability to raise welts on their skin, so they can change their microshape. So they can kind of bring up these textures. So they have texture mapping, and so they have shaders and texture mappers, as we'd say. And then they can rearrange their tentacles to get gross shape changes. So they can really turn into different things. It's the weirdest thing. You can watch this octopus, and then it turns into a fish. And it's just like, it really looks like the fish. Or if they want to do camouflage, they're just impossible to detect. And Roger once did a thing where he put a cuttlefish he made a fish tank with a display on the bottom, and he put a chessboard on the thing. He put a cuttlefish on it, and then it put up the chess square, so it disappeared. Then he rotated the chessboard 45 degrees, and it rotated. So when they do their camouflage, they're scene aware, and they do it in great detail. And the other beautiful thing is they don't just do it for these very functional things like camouflage. They do weird mating dances, which are these like psychedelic extravaganzas. And they're very hard to follow sometimes because you see them turning into each other, and the males turn into females, and they turn into other creatures, and there's all this color, and there are these waves of color flowing from one and then onto another. Now here, of course, I'm probably projecting. I don't really know what's going on with them. I don't know if they're experiencing some psychedelic joy or if it's just all some automatic pilot. Not enough is known, but it's wonderful to see. So this led me to this sense. Well, first of all, a very reasonable question is why aren't cephalopods running the world? And there's a very interesting reason, which is they don't have childhoods. Their reproductive cycle is that each new generation learns a great deal. They can become remarkably smart, but they don't pass anything on to the next generation. It's one of those things where the males kind of die. They're not eaten by the females or anything like that, but they just kind of fade away. Once they mate, that's it. It's like they're just out of there. And the females lay eggs, and the hatchlings are just off on their own. They fend for themselves. So there's no intergenerational heritage. And there's no neoteny. is what we would say. With people, like we've raised neoteny to this level of obsession where we just refuse to grow up entirely at this point. And it's true. We're turning adulthood into a new form of childhood, right? That's what civilization should do. That's what comfort should be like, I guess. So, but they have none of that. So on the other hand, they have wonderful brains, and they have this, they have naturally occurring virtual reality systems. They ought to, if they had an ability to pass information from generation to generation, they would have this expressive system that my sense is fundamentally superior to ours. So it would be really quite dramatic. So the equation I have in my book is, let me see if I can remember this. It's hard to remember equations perfectly, but it would be cephalopods plus childhood would equal people plus good virtual reality. Something like that. So, so there's sort of two ways to fix all of our problems. We either have to re-engineer cephalopods to have childhoods and intergenerational culture, or we have to fix virtual reality and get it to work well. So, I think both are good programs. You know, I'm just working on one of them. But shall I cease, David, or shall I?
It's probably about time.
Yeah, I know.
I know.
What?
I know you don't have anything more to say.
I'll
save you.
No, see, the thing is, David has had to make me stop speaking longer now, so like 3 times in the last week or something. So I wanted to save him the trouble this time and make it easy.
This time you have a musical chance to return.
That's very true. That's very true. Well, we thank you so much for. Questions if you want. So, yeah.
Is there 4 colors the same as our 4 colors?
No, their 4 colors are not quite the same as ours. They overlap. But actually, a lot of the cephalopods that can display colors we enjoy can't see them quite. And but what they do, it's a little bit complicated. Sometimes they can see polarization in a way we can't. And their colors might correspond to polarizations that they really care about in a particular environment. So they often can't see everything that we enjoy and what they do.
Hi, I have the mic. It's a pretty adaptive thing. You hold it in your hand and you get the mic. There was a period when people were investigating the imaginations of mathematicians and physicists, and a lot of them had very visual imagination, apart from their ability with algebra. And when they talked to Einstein, he almost uniquely said, "Oh, I think of the fields in gravitation with a kind of synesthetic," and he did this strange kind of movement in the interviewer where he said, "I feel it flowing through my body in some odd way." Which suggests that if we had a virtual reality with feedback would be even better if the suit responded to you.
Right, well, it's funny, that Einstein anecdote is brought up to me about once a week, and I believe it's quite true. And I've known a few people who knew Einstein, and they all have said that he would say things like that. I'm a little, part of me is saying, okay, wait, pull back on this, because a lot of technologists and scientists are a little bit too quick to say, and all we have to do is make this connection, and everybody will be Einstein. I doubt it's that simple. It never is. But I do think there's something there. Yeah. You have to yell.
How is it with the cephalopods, they had such an immediate ability to translate what they see into the...
How is it in the cephalopods, they have such an immediate ability of translating what they see into the textures and patterns on their skin? I mean, how the rapidity with which this happens, and also the actual mechanism by which it's translated into through the visual cortex and then back out.
Yeah, they have their neurology is really cool. They have a visual expression lobe. Just like we have specialized parts of the brain for control and so forth. They have this part of the brain where the surface of it is approximately the picture that will show up on their body. And they also have, as is widely celebrated, they have spectacular eyes that don't have blind spots. And they actually have a fairly easy mapping thing on one level, but the theory of mind stuff and the orientation to the environment is the stuff that startles everyone. And that's the stuff that's not as well understood. And perhaps we're a little vulnerable to sometimes wishing them to be smarter than they might be because we so much want to believe in I'm sure I'm guilty of that, but I'm not a marine biologist, so I can get away with it. It's only Roger who get in trouble for giving this talk, but I can. What's interesting about it is the mapping is probably not as remarkable as some other mappings within brains, but the sort of executive oversight and the higher level control of it is the thing that's really just startling.
Thank you. And I just wanted to know, what does the future of virtual reality look like to you now?
Well, all right, so I'm in a weird position where I still really want to get things out to people. So I started working with one of the tech companies, and we had one great success with something called Connect. And the usual suspects will be doing other things, and that's kind of all I can say. Well, Google just made a fuss about their thing, but you know, some things will happen.
Are you excited about it?
Oh, it's deadly dull. I wouldn't be. No. We'll see if we can do it. You know.
Thank you, Jaron. It was a wonderful presentation. Can you talk a little bit about how maybe we've overrated the intergenerational influence on neonates' cognition through the direct linear parental-child, and how it works socially in that, I mean, that's why it's interesting to have these feedback loops with things, and that cultures under the water or over the water, terrestrial or aquatic, have a lot of things around which, you know, we respond to, we think through, we think with, so that it's feasible to me that the kinds of ideas and intelligence and responsiveness that, even though these cephalopods don't have childhood, they have environments within which information is transmitted and socially.
The adults don't encounter the kids. I mean, they really don't. There's not even, like in our case, as a parent, I know how tenuous this parent-child link can be on occasion, right? But the thing is, collectively, there's tremendous contact, but not in the cephalopod world. The kids, they come out of their egg and they're just kind of off. They don't really encounter older ones, or it's random and unlikely, and they're pretty sparsely placed in their own environment. So it's not like our situation where there's sort of a larger population effect of transmission of information. It's not like that, so far as anyone knows. Remember, these are not creatures where there's huge hordes. These are rare creatures. These are smart creatures that are sparsely distributed in their environment. So each one has to learn their own way. Or so I think. Yeah.
Thanks a lot.
Thanks a lot, Jaron.